here's the video for the rest of the chain rule. And so we're just gonna do finding an equation of a tangent line, which you guys have done a lot of. We're just gonna do a problem where we're gonna have to use the chain rule. So here, anytime we're asked to find the equation of the tangent line, we can find the derivative and then substitute in the x value at into that function to find what the slope of the tangent line is at this point. So we're going to differentiate. So y prime is equal to the constant multiple e to the 4x, right? E to anything is the same, but then this is my inner function, the 4x, so I'm going to multiply by the derivative of 4x, which is just 4. So y prime is equal to 20 e to the 4x. Okay, now we want the slope. So here's my derivative function. The slope of the tangent line at the point 0, 5, I need to plug in 0 for x. So when I substitute in 0, we've got 20 times e to the 0, right? 4 times 0 is going to be 0. E to the 0 is 1. 1 times 20 is 20. So the slope of our tangent line is 20. So we're going to write y minus our y-coordinate equals the slope of 20 times x minus the x-coordinate. We can leave it in point slope form, or we could convert to slope intercept form, which is going to be y equals 20x plus 5. So either of those would be sufficient for the equation of the tangent line. So we've done a lot of this. We're just differentiating now with an additional tool, the chain rule. Okay, now we can also combine the chain rule with our other rules, such as the product rule or the quotient rule. And it doesn't matter too much the order in which you do it. Sometimes you'll find that one is going to be more efficient and faster. For me, when I see this, right away I see a product. I see e to the x times this function. So a product, right, if I'm finding a product here, when I differentiate, I take the derivative of the first times the second as it is, x squared plus 1 to the third, plus the first function as it is times the derivative of the second. Now, this is a composition of two functions, so I'm going to use the chain rule here. So, the outer, right, I bring down the 3, keep that inside function the same, drop our exponent by 1, and then I'm going to multiply by the derivative of the inside, which is going to be 2x. Now, this is all multiplication, and the order in which I multiply does not matter, but I do have to be aware that this addition sign is kind of separating this term from this term, okay? So, there we go, okay. Make sure I'm writing along the same thing. So here we kind of did the product rule plus the chain rule. All right, and I am going to go ahead and just clean this up a little bit, you guys. So what I'm noticing is that both terms have this. They have an e to the x and they have an x squared plus 1. This one has an x squared plus 1 squared. This one is to the third. So I can take out an e to the x and an x squared plus 1 squared. Okay, so if I factor that out, here's what would be left. So in this part, I would have left an x squared plus 1, right? And then out of this one, we'd have the 3 times the 2x left, which would be 6x. So this would just be a little bit cleaner way to look at it. Again, depending on what you're asked to do, multiple choice, your answer is probably going to be presented in a form that looks more like this. On a free response, this would be a totally sufficient answer. Okay, number 3. Now I have a composition that involves a quotient, but again, the quotient's kind of happening inside. It's my inner function, so I'm actually going to do the chain rule kind of first. I'm going to bring down my 5. And keep my inside function the same. And then drop my exponent by 1. Okay? And then times the derivative of the inside. So the inside's a quotient, so I'm going to apply the quotient rule. So the derivative of my numerator is going to be 3 times the denominator as is minus the numerator as is times the derivative of the denominator, which is going to be 8x, all over the denominator squared. Okay, and again, depending on what we are asked to do, I'm going to show some simplifying just because I think it's helpful to practice. I would encourage you guys to practice simplifying on the homework, and then on tests or like free response practice, don't practice simplifying there. But it's good to get in the habit so you feel good with your algebra manipulation, and then you're able to get to the point where you're going to see the multiple choice answers match your own. Okay, so for simplifying here, I'm going to kind of rewrite this part. The fourth power is applied to both the numerator and the denominator. So I'm just going to kind of write it like this. Okay, and this is 5 over 1, so that's kind of why I broke that down here. If I distribute some pieces here, I'm going to get 12x squared minus 15 minus 24x squared, and then minus 16x all over. I'm going to leave the bottom here, 4x squared minus 5 squared. So look at my denominators. When I multiply, those are the same bases, so I can add those exponents, and then I can just clean up the top a little bit by combining some like terms. So I've got 5 times 3x squared plus 2 to the 4th. Here we can combine those to get negative 12x squared and negative 16x minus 15 all over 4x squared minus 5 to the 6th when I add the 4 and the 2. So this would probably be the form again that our multiple choice answer would be in. Okay, last one here, you guys. We have worked on finding the derivative of exponential and natural log functions. In this chapter, we're going to expand to all exponentials and eventually to all logarithmic functions of any base. We're not going to get to logarithms today. We're just going to talk about exponential functions of any base. So we've done e, but we haven't done other bases. So for example, we're going to do this one where I have 3. So here's kind of the rule. It's going to be the same exponential function as is times the natural log of its base. Now, if it's not just x in the exponent, we do have to use the chain rule. So in this one, the outer function is just 3 to the x. So the derivative of 3 to the x using this rule is 3 to the x, but we're keeping our argument whatever it is, times the natural log of our base, which in this case is 3. Then because of the chain rule, since this isn't just 1x, it's a negative 1x, we do have to multiply by the derivative of that exponent. The derivative of negative x is negative 1. So again, clean that up just a little bit. We'd get negative 3 to the negative x times the natural log of 3. All right. Okay. This last one, again, we're going to use the chain rule because it is an exponential function composed with a polynomial. So the outer function's the exponential. So I'm going to say that g prime is equal to 1/2 raised to the, keep the exponent the same, x squared plus 1, times the natural log of our base, which is 1/2. Okay, times, using the chain rule, the derivative of our numerator, which is 2x. Okay, so again, I'm going to just show some simplifying here to just practice getting some of our algebra skills. So remember when we multiply things that have the same base, we add the exponents? So I'm actually going to break that apart into that multiplication. So I'm going to write it as 1/2 to the x squared times 1/2 to the first, right? So if I put that back together, it would be this. And then still times natural log of 1/2 times 2x. Okay, so 1/2 to the first is just 1/2. And then I can multiply 1/2 and 2x and get 1x. Then I can also apply that x squared to this whole fraction. So 1 to the x squared is just 1, right? 1 to any exponent is 1. And then 2 raised to the x squared, okay? And then times x, right? Because I put this part and this part together. And then times natural log of 1/2. Okay, so again, just a little more simplified, I can say x, right? This is like x over 1, so I can multiply those together. X over 2 to the x squared times natural log of 1/2. And that's about as clean as we can make it. So likely our multiple choice would look very similar to that answer. All right, guys, that is it for the second channel video. Thank you for watching.